Welcome to Spring LIB.
Hello everyone, today we're doing chapter 11, problem 40, and this problem gives us the products of various chemical reactions and asks us what alkyne starting material will give the following ketones after we do a hydration reaction with water, a strong acid, and mercury. So this is retrosynthesis. Remember, let's start with A. We're trying to find this as the product. So we draw our retrosynthetic arrows to work backwards. So we know that we need start with an alkyne, so we know that we should start with the same number carbon alkyne. So 1, 2, 3, 4, 5, 6. So we have 6 carbons. So 1, 2, 3, 4, 5, 6. And now we know that we added an oxygen to it on carbon 2. So how can we add an oxygen on carbon 2? Well, we know that if the alkyne was here, then carbon 1 would have more protons. So following Markovnikov's addition, this side would get the more protons. This side would get, carbon 2 would get your carbocation intermediate, which a nucleophile can attack. And our nucleophile, in this case, we would want to be water. So we know that alkyne exists on carbon 1, 2, and not carbon 2 and 3, because then carbon 2 and 3 are equivalent with number of protons. So then you would not get any specificity for getting this only one product. So that's what the question says. We want only this product identified. So now, how do we know that this is correct? Well, let's work through it. If I have this alkyne and I reacted with water and acid and mercury, well, we know that the hydrogen will get picked up through this carbon. So if you have OH2, the hydrogen will get picked up on the side with the most number of hydrogens. And that leaves us a secondary carbocation where the OH minus can then attack. Remember, there's acid, so there's actually an equilibrium with H2O and H3O. So there actually wouldn't be any OH minus here in a solution, but I'll do that for simplistic sakes. And now we have an enol tautomer. So we want the keto tautomer. So all that needs to happen, we do keto-enol tautomerization. So we use one of those lone pair electrons on oxygen to make a carbonyl bond. When we make a bond, we break a bond, that'll pick up this proton, so oxygen stays neutral, and with giving us 2 electrons to the oxygen nucleus. And we're left with this carbonyl in problem A. So we know that, yes, this is indeed the right starting material. So now, B, we want this product in B. And we need to find what alkyne starting material gives us this B. So same thing, we have a secondary ketone, or just we have a regular ketone in carbon 2. So we know that an alkyne is a triple bond, and we have 3 carbons. So let's draw 3 carbons, and then there's only one option for alkyne. We could either draw it here on this side, but then if we flip it, it would be the same thing. So they would be identical. So this problem is actually giving us the answer because it's telling us that we want an alkyne starting material. We have 3 carbons. So there's only one possibility for this to exist. And if we follow this mechanistic route, we see that the alcohol would attach here, and then you can do some keto-enol tautomerization to form this ketone product. So for C, you're given a cyclohexane with an exocyclic ketone. So if I do my retrosynthetic product, so this is the product we want. And we need to identify the starting material we need. So remember, I always like going from, so there's 2 ways you can approach this. So we approached it by counting the number of carbons. So we approached it like this, counting the number of carbons, drawing your starting material with the number of carbons, and then add your alkyne bond to where it makes sense that you would get a secondary carbocation on the position you want your nucleophile to attack, nucleophile being oxygen. So we know we want oxygen attack here, so my carbocation has to be here. So I need whatever side that's adjacent to it to have less number of carbons, less number of protons than this side. Well, this side currently would have 2 protons, but this side would have 3, this side would have 1. So obviously the side with 3 protons is the side that's going to get my alkyne bond, because then when you add alkyne, it still remains to have 1 proton, but this has 0 protons. If I were to add the alkyne bond on the other carbon, you'd see an issue with that. This carbon now has 5 bonds. This is not possible. You would not be able to get an alkyne bond here. So we did this problem doing this method. This is kind of a shortcut, but another method we can do is work backwards. So this is the final product. So let's work backwards. So how do we get to this? Well, this is the ketotautomer. So let's draw the enotautomer. So oxygen with the lone pairs electrons can pick up a proton, making a bond. When you make a bond, you break a bond. So the sigma bond between carbon and hydrogen will break to form a new pi bond here. When you make a bond, you break a bond. So the carbonyl bond will go up to oxygen nucleus. To make sure that we don't have a carbon with 5 bonds. And now, as you can see here, we have our enotautomer. And how do we get this tautomer? Well, we have to add water to an alkyne. So we see that right away by the tautomer being the pi bond of the tautomer be on this side. We know the alkyne also has to be on this side. So D, we'll draw D on the separate page. So 1, 2, 3, 4, 5, 6. 1, 2, 3. So we want a carbonyl here. So this problem is a little bit more tricky. We need to identify how can we get this product from our alkyne starting material. So we have 1, 2, 3, 4, 5, 6. So we have 6 carbons. This ketone is placed directly in the middle of this. So it's on carbon 3. 1, 2, 3. So we have it on carbon 3. So how can I get addition such that I would get a nucleophilic addition on carbon 3? Well, it'd be more simplistic to go through the routes of working backwards. So let's do that. So let's do the keto-enol tautomerization. So we have 2 routes. Oxygen can pick up this proton, make a pi bond here, and break this carbonyl bond. So then we get our enol tautomer here, and therefore it would tell us that the alkyne has to exist on this side. Or 2, we have another beta proton, so the oxygen, can pick up this proton, make pi bond here to kick up our carbonyl. So then you have your ketone on this side, your pi bond alkene on this side, your alcohol here. So that would tell us that we have an alkyne between these 2 carbons. So let's count. We have 1, 2, 3, 4, 5, 6. So we have a 2 alkyne, but here we have a 1, 2, 3 alkyne. So here we see that neither side has any protons. So if I were to add my water and acid, there'd be no preference actually to which side it would attack on. So with equal chance, the proton can be picked up from this side to give a carbocation on this bottom carbon, which is what we need, this carbocation to be on carbon 3. So then we can make our alcohol and then reduce and then oxidize it to a ketone. But possibly, if you pick up the proton on the other side, we'll form an unwanted product with the carbocation now on upper carbon. So then we'd form the wrong product. But remember, the question stem says you only want to form this correct product. So we know that this right here cannot be the case. So let's investigate the bottom method. So we add the same reagents. And let's say, once again, there's 2 options. They're equivalent because there's no protons and Markov addition fails here. We get a carbocation here, which we could call 1, 2, 3. So after we add in our alcohol, you would get an alcohol on carbon 3, which we could oxidize to keto-enol tautomerization to its keto form. Well, what happens if we pick it up the proton on the other carbon? So we pick up the proton on the other carbon. Then remember, you get your proton here, then you get your carbocation on the opposite carbon. But still, if I count from the left, 1, 2, 3, this would still give me a carbocation on carbon 3. So if I add my alcohol, I would still get my alcohol on carbon 3, which will go to tautomerization to form ketone on carbon 3. So we know that this indeed was the product.